Okay, so I hear you asking, Digital Asa, how do we measure things? The short answer is with tools, right? We have different tools that can measure different things. Um, they scale from robust to pretty simple, like a tape measure or a scale or a beaker for weight, distance, and volume are all pretty simple. Something electronic that does some calculations under the hood and gets a little bit more complicated, like a multimeter or a spectrometer, can work too to give us values for stuff. This, by the way, is a spectrometer. It measures wavelength or frequencies of light, energy levels of light too. All right, so when we're measuring stuff, sometimes we'll end up measuring things that are very, very big or very, very small. For instance, if I wanted to look at the size of a single atom, I'm going to end up getting obviously a very small number if I'm measuring it in common units. Um, Likewise, if I asked you how much water was in the Pacific Ocean, then obviously a lot, right? It's going to be a very big number if we're using gallons or liters or something. So we have a way of writing big numbers and small numbers to not have to worry about moving all those zeros around. You might make a mistake that way. You also might, it's a pain to write out all those zeros every time. So we can show scale using orders of 10. For instance, the observable universe, is about this big. In meters, its distance is this number, um, which is thousand, million, billion, trillion, quadrillion, pentillion, heptillion, sorry, hexillion, heptillion, octillion. So it's 880 octillion meters across. Um, Writing that number out every time is really annoying. So what I can do instead is I'm going to put a decimal point between my two non-zero numbers, put a decimal point after the first number that's not zero, and I'm just going to multiply it by 10 to whatever power to make this number a lot easier to digest. So I can just call this instead, and call it 8.8 times 10 to the 26th power, which means I'm multiplying 8.8 by 10 26 times. So we can use this to represent scale way easier. The shorthand for this also is moving your decimal point. So if I want to figure out what I would write this in scientific notation with, I would move my decimal point over until it reaches between my two eights here. So my decimal point obviously is going to be right here. Normally, I would move this over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So that's how we know that it's 8 times 10 to the 26th, or 8.8 times 10 to the 26th, excuse me. Negative orders move it to the right one plate, to the left one place, excuse me, and positive orders move it to the right one place. So big numbers we get from positive orders of 10, small numbers we get from negative orders of 10. Okay, this brings us to our first Dora the Explorer problem. I would like all of you to please, right now, pause the video and try to convert all these numbers to and from scientific notation. So pause the video, give that a shot, and then come back when you're ready to see the answer, see how you did. Okay, so now that you're back, let's take a look at the answers to this question. So here we've got 9,070,000. I want to put that in scientific notation. We're going to put a decimal point after our first number that's not a zero, and we're going to count how many places we moved it. So that is 1, 2, 3, 4, 5, 6. So this is a big number. We're going to use a positive order of 10. I moved it 6 times. So this is 9.07 times 10 to the positive sixth. Our next example, again, put your decimal point after the first number that's not a zero. We have to move it 1, 2, 3, 4, 5 times. It's a small number, so it's negative power. That's 3.45 times 10 to the negative fifth. Here, I'm going to move it between the 8 and the 3. That's 1, 2. It's 8.376 times 10. I moved it twice, and it's small, to the negative 2. Here, move between the 5 and the 7. 1, 2, 3. That's going to be 5.670 times 10. It's a big number to the positive third. Okay? Likewise, we can work backwards when we're using scientific notation to standard format. So here, my decimal point is at 9.678. I can move this 4 times because I'm multiplying by 10 to the fourth. It's going to be 1, 2, 3, 4 times. And every blank space you get, like this blank space I have right here, that blank space gets filled in with a 0. So we end up getting 96780, 96,780. Here, here's our decimal point. We're going to move it. It's negative third, so we're making this number smaller. We're going to move it 3 times to the left. So that's 1, 2, 3. Fill in our blanks with zeros. We get 0.0074521. Here, 10 to the 7th. We're going to move this guy 7 times. Positive exponent, so it's becoming bigger. 1, 2, 3, 4, 5, 6, 7. Fill our blanks in with zeros. So it's 851, 1, 2, 3, 4, 5 zeros, 85,100,000. And then lastly, 4.09 times 10 to the negative fifth. I'm going to rewrite this over here. So I space. Negative fifth means I'm moving this 5 times. 1, 2, 3, 4, 5. Fill in the zeros, we get, and this one, we get 0.0000409, which is this one. Cool. Okay, so pretty simple. Again, this is something you've probably already done in a previous class you've taken. This is something that I teach to my ninth graders in high school, but that was a while ago. So maybe you haven't dealt with scientific notation in a while. Good to review.